Good morning, everyone. This is Yahia Farid, and I'm here with my colleagues Ahmed Abo Ahmed, Ahmed Leithy, and Yusef Koura. And today we're going to be showing you our progress throughout the semester. Okay, so just as a quick refresher, uh, our um, our thesis proposal is to develop an AI agent that would be generic enough to play any 3D platformer, and this would essentially be a component that can be bought off of the Unity asset store and can be used by Unity developers in order to test their games for any potential bugs or hidden mechanics. So if we look here, these are our progress targets. We're going to be talking about each one individually to explain the different milestones that we achieved throughout the semester. So for the first one, the first thing that we had to do is to basically find an open source game that we can train our model on. So after finding an appropriate game, we started to create different levels, and we wanted to adopt curriculum learning in which we expose the model to levels of increasing difficulty. So as you can see here, we created the 3 different levels. The first level is just a very simple level where the player starts from the pipe, as you can see here on the left. And then all he has to do is basically walk forward to the goal, which is indicated by the sign. Level 2 is a bit more complex. We didn't want the model to just learn walking forward, so we have this map where the player can spawn in 4 different locations. He can spawn in the pipe on the right, on the far uh, top right, and on the left, and you would just have to walk to the center where the goal is. And then finally, the third level is a bit more complex. We have spikes now, so these are kind of like a danger to the agent, and then he has to jump over these 3 obstacles at the end in order to reach the sign. We also implemented coins, however, they're not currently shown in these screenshots, but we're going to be showing them later on. So the levels we showed in the last slide were only used for training. So we also wanted to develop a blind test level. This level was going to be used at the end in order to show how the model is going to perform on a level that he has not seen before. So as you can see here, the level is basically the model spawns from the pipe, and then we have some obstacles, some holes in his path, and then he has to reach the sign that is located at the far end of the map.
Next, we wanted basically to develop our agent, as mentioned before, to play any 3D platformer. So when developing basically the features that would be fed into the model, we wanted to make sure that the features were environment independent, i.e., they would work basically for any game. They weren't dependent on the specific game that we had found. To that end, we first had to develop special sensors in order to be able to give it the proper information that it needs. So the framework that we were using, ML Agents, actually provides these raycast sensors that you can see in red right here and in green. Basically, they are just simple rays that protrude out of any object that they are attached to, and they have many parameters that can be set that dictate their angle, the number of them, and how far and how big their receptive field is, basically. So you can see here we set up 2 layers, one red and one green. The red layer is basically just radially around him in the same level as the agent, and the green ones are basically angled a bit upward in order to be able to detect objects that he might need to jump over, let's say pipes or certain obstacles. Basically, the information provided by these raycasts is that when they hit, they tell you whether or not they hit something. They tell you the normalized distance between the object and the object that they are attached to and the object that they hit, and they return a one hot encoded array that is basically contains a set of detectable tags that we give it. So let's say in this example, our set of detectable tags are enemy, finish, and platform. So in this picture, the raycasts are hitting a finish sign. So it would return an array that is 0 everywhere and gives a 1 at the finish to indicate that it has detected an object with the finish tag. This is basically the set of information provided by the raycast.
So the idea is when we thought about it is that we want to give our bot as much information about the environment as possible without being dependent on it. So since raycasts are independent of the environment, we felt like we need to give them more information to overcome the obstacles of 3D platforms, such as jumping from places, jumping over like a spike, or going to a different platform through some kind of steps. So the idea is, and we had to improve upon the ML agent structure. And as you can see here, this is like the simplified sensor ML agent provides, which is like the base component sensor. And we have like the 2D and 3D component. For our use, it's and in the rays you've seen, we use the 3D component for the horizontal rays, but we felt like we need to give him like some vertical rays to give him like as much information about what is he's like seeing, what could be like on the sides, and what is possibly like a hole in front of him. This should help him and visualizing the area around him. For our progress presentation one, this was our first iteration of like the vertical sensors, and we found out that it could be like insufficient, as it had like one major issue. The issue is that like when we rotate like the player at some direction, it would rotate with him, and that would like give the bot like misleading information about his position in like the world of the game. So for that, we had to improve upon it, and we had to like make the vertical sensors in like a constant manner. And for our second iteration and the current one in use, the the um, the idea is that now we had to make the vertical sensors to be in like a constant manner, even if like our bot rotates elsewhere, it's always in the same constant way, which should give him like the physical the actual like values of the positioning, even if he rotates at any position. So, in addition to that, we felt like we need to give him like more information, and for that we had to feed like the sensor input, and in addition to that, we had to add our vector observations, such as like giving him like a vector that is called as grounded, which should like reflect upon the tag of like the object beneath the player, and this should give him like an idea of where he's standing, what kind of a platform he's on, and the type of object that is beneath him.
After we had decided on how we would feed the features into the model, we decided that we wanted to use imitation learning. Why did we decide to do that? Because basically we would start training the model, and if we had started training the model just from scratch, the training might have been ineffective. It might have taken a very long time because he would be basically learning from absolutely no knowledge. He has no knowledge of anything. He would just be trying from very basic things. To address that issue, we wanted to give him a little bit of pre-training, or at least a little bit of pre-information before he started training. And to do that, we found that ML Agents provides a means of utilizing imitation learning, which allows the agent to learn from demonstrations that are recorded. So basically, to achieve that, ML Agents provides a few things. First of all, it provides a demonstration recorder component. We use that to basically record our demonstrations. We attach it, turn it on, set a specific number of steps, and then we start playing the game. While we're playing the game, the demonstration recorder basically just records our gameplay and finally outputs the .demo file, which can then be given to the model when it starts training. The way it utilizes these .demo files comes in one of two ways. Either generative adversarial imitation learning, which is called GALE for short, or behavioral cloning. We mainly relied on GALE because GALE doesn't need as much data to be able to give enough information to the model. Um, the way Gale works is actually similar to how deepfakes works because it's a GAN essentially يعني. And essentially it has a discriminator which takes the demo files, which have like the specific information of how we played, and it takes the actions of the agent. It then compares the actions that the agent has taken to our demo files, and as yani, it basically gives us a reward the more it is similar to how we played. The less it's able to discriminate between our gameplay and the agent's gameplay, the bigger rewards it gives to the agent, essentially يعني leading the agent to play more like we play. The second method, behavioral cloning, we tried it for a bit, and we tested a few models using it, but they produced some suboptimal results, and we later realized that it had actually deprecated and wasn't compatible with all the modes of operation in ML agents. So we just scrapped the idea of using it.
Okay, so to be able to have the model in the game, we needed a way of abstracting the character's actions. So a player in the game can take inputs from either the player or the model. So the character itself can move depending on the player's inputs or the model's outputs. So the way it usually works in Unity is that there's a script defined by the developer, usually a C# script, and it takes inputs to a static class in Unity known as user input, which basically defines what keys are being pressed right now. So usually the component would involve some statements that declare that if, for example, a specific button is pressed, then the player should behave in a specific way, or the model should move in a specific way, or jump, or etc. So we needed to be able to have this same result, but not from the user input. We wanted to also take inputs from the output of the model itself. So we developed this abstraction class known as that we called agent input, which basically can be accessed from anywhere, and it can take its inputs either from the user or from the model itself. And without any changes to the developer-defined component, it will behave the same way, not knowing where it's getting its inputs from, whether it's from the model or from the user. So this makes things a lot smoother because the developer doesn't have to change his code, or like doesn't have to change his code in any major way to be able to install the component on his player object. And at the same time, it also makes our lives easier because we don't need to care about the developer's actual component or how it works to be able to implement our model into the game. But we also realized that we need the developer himself to be able to give specific rewards or punishments based on how the game works. For example, based on collecting coins or whatever it is the objective of the game is. So we added this extra feature that allows the user to define his own rewards and add them to the agent input, and then the agent input himself would, like the class itself would propagate these rewards all the way to the model without the user having to worry about the process itself.
So for our rewards and punishments, we had to define a certain set of rewards before we actually started training our model, so that we would allow basically our model to learn somehow using a certain set of rewards. So for the rewards, we have two sets of rewards. We have extrinsic rewards and we have intrinsic rewards. For the extrinsic rewards, these are the rewards that are related to the environment and how the agent deals with the environment. So you can say that they're sort of like related to accomplishing certain tasks. So for the rewards that we have a reward for winning. So for example, if the model reaches the finish line, he gets a big reward. And for any coins that are spread out throughout the map, if he collects any of them, he also gains a small reward. As for the punishments, we have a punishment for losing. So if the model falls into the water, he loses a certain amount of reward. And we also have another parameter that we have defined for the developer or the user using our component, which is sort of like a time to finish the level parameter. And by setting that parameter, the developer is basically declaring a certain time that he wants the model to finish the level in. And if the model takes too long, then it would gain a punishment because it is taking too long to finish that certain level. As for the intrinsic rewards, we have other sets of rewards. So for example, Gale, which was mentioned by Yusuf earlier, gives the model an intrinsic reward based on the similarity to the demonstrations. So for example, if the model is performing in a way that is very similar to our demonstrations that we have recorded, the model would gain a positive reward since it is as you can say, imitating what we have done before. We also have another intrinsic reward from a module called the curiosity module. And this is basically, it rewards the model if it decides to explore more. So essentially, when the model is trying to predict an action to take, when it has decided to take an action, it tries to predict the outcome of that action. If that outcome of that action is the same as the one that it has predicted, then it gains no reward. However, if the outcome is different than what it has predicted, then it gains a small reward, because it is essentially meaning that the model is exploring different or uncharted action spaces. And then for the final punishment, we have an intrinsic slowness punishment, which is different than the one I have mentioned earlier, which is the parameter that is defined by the developer. And this is a small punishment that we give the model if the model decides to just wait around and do nothing, or if it's moving very slowly, in order to try and promote the model to win faster than usual.
After setting up all of that, we now come to the part where we actually train the model. To that end, basically, training in ML agents basically involves just defining a config file, setting up all the components in Unity, as can be seen to the right in the video. And then we just type a command in the command line and hit play on the Unity editor, and that starts the training. So with regards to the configuration, we set a few things. I'll just highlight the most important ones. First, we pick one of two algorithms that it uses for training, either PPO, which is proximal policy optimization, or SAC, which is soft actor critic. In soft actor critic, there is basically two networks, an actor network and a critic network. And in the proximal policy optimization, it basically has a certain policy that acts upon and keeps trying to optimize. We also have some like the basic neural network hyperparameters like batch size and learning rate and so on and so forth. We also set like things like the hidden layers and all of that. The more interesting parts are, for example, the memory. We can set a memory, which is basically a recurrent neural network, where we can define a specific memory size to dictate how much information it retains, and a sequence length to basically say how long of a sequence of actions it actually remembers. Next, we define the reward signals, which are things that are like the ones described by Yahia, like the curiosity module and the Gale module. For things like that, we can just dictate a certain strength or certain parameters that basically say how strongly these things give rewards to the model or give punishments. And yeah, that's basically the training configuration.
So we're going to give you a glimpse of the results that we were able to produce, and we're going to talk about the future work as well. So this is the kind of progress that we had made by the start of Progress Presentation 1. And this is on level 1, if you remember. And basically, we can see here that the model does actually win, but you can tell that it's kind of jittery. It's kind of unstable. It's not really decisive. And we realized that we had not been using Gale to its full extent at this point. So past Progress 1, we strengthened Gale. We increased the strength parameter that Yusuf mentioned. And we can tell instantly that the model became much smoother, much more player-like, much more like our demonstrations. Which is a good result. And then we tried to make sure that it's not overfitting by making it at a slightly different position. And we noticed that it was actually still converging towards the goal, which we thought was impressive. And then we thought we'd try to like mess with it a little more. And we added like a few blocks of blockades in the middle. We were really surprised when it actually managed to jump over them, because this had not been part of its training. It had only been training on level 1 without the blockades. So we were impressed by that. And then we moved on to level 2. Where we can see that it after we had to adjust the parameters quite a bit, but we in the end, after we recorded a couple 100,000 steps of demonstrations, it was able to actually beat the level starting from any position. We can also notice here that the coins are spawning randomly, and this is something that we decided to do at the beginning. But then we realized that it's not really converging towards collecting the coins, and this is something that Dr. Sharara mentioned as well. And we ended up not using this random spawning technique because the model doesn't always try to collect the goals like you see here. It just walks towards the end instead. And then in order to prepare the model for taking the blind test, we just designed this level that contains a lot of platforms, as you can see, like about 5 platforms and about 9 different starting positions. And we trained it on this for a long time. And we also like recorded demonstrations of our own to help it with the training. We haven't yet adjusted all the parameters for this, so the result is not exactly ideal, but it's still something that we think is pretty good, considering that it has never seen this blind level before. This model is a little careful, so I'm going to increase the speed a little bit. So here, as you can see, it's trying to walk towards the goal at the end, which is behind that wall, but it's being very careful about not walking through these obstacles, and we were almost impressed by the fact that it's avoiding these obstacles that it has never seen in this exact position before. And it manages to jump over the wall and get on the same platform as the goal, but then at the end it ends up suiciding on the top right corner. And I think with a little bit of adjustment and a little more tuning, we'd be able to get it to actually beat the level without seeing it. And that's one of the things that we want to do for thesis 2, which is adjusting the model's parameters and working a little more on it and making sure it actually can beat these levels. One of the things we've been struggling with is a problem known as catastrophic forgetting, where after the model is trained on a specific level, if it's trained on another level, it tends to forget the old level and how to beat the first level and how to deal with the obstacles that it met before. We thought we'd be able to get over this by just putting it back in the old level and then it would remember, but it seems that whenever we do that, it just forgets the new one again, which is one kind of problem that we're going to try to address in the future. Hopefully after that, we'll be attempting to test this same model on different games using the same, exactly the same features so that they're independent of the environment, and we're expecting that it should behave similarly, and if we're able to do that, then we've done some good work here.
So for the final part of our presentation, we want to talk about the empowerment outcome. With the current results, even though we haven't really trained it that much on the blind level, we're seeing like promising results, and that like is pushing us towards the idea of making it as a full component that gets integrated into Unity. And as you can see in this image, like the current UI system is that it gets integrated into the Unity editor UI. And you can see here we have like our own scripts that is like integrated in the system, and you just like plug in the parameters. And in the next image, we're gonna show you like some of the tags that we're using. As you can see here, we can define the size of the tags, like the number of objects that the sensors are supposed to detect, the type of objects. We name them by like, you can pick whatever name you would like for them, and based on that, our sensors can like detect whichever object we're interested in the scene. And also like we have variable parameters for like the amount of sensors, like if we need to increase it, decrease it, if we want like to maximize the amount of sensors, which is very beneficial to give information to the sensor. And for the idea of how to publish it, we're expecting that we're going to publish it on the Unity Asset Store, which is like part of the Unity system, where you can like publish your component, and all you need to do is just to like just purchase it. And once you buy it, like you can and like install it, it gets integrated immediately into like the package manager. The package manager is part of any project that you work on Unity, and you can import packages just by like picking their names. And with that, we wrap up our presentation. Please feel free to ask us any questions, and thank you.